Hi, let's have a look at this question, and you can see it's a very simple question. And the question is the reagent for this conversion uh, is or are. So now you can see the reaction given to us is we have 1,2-dibromoethane, and it is made to react with a reagent, which is what we have to find out. And what we are getting is alkyne, isn't it? Very interesting question. So first of all, one important thing that you should understand here is Br is not present in product. Br is not present in product, isn't it? Which means Br is getting eliminated. All right. So the key here is we have to go for elimination. All right. So now let's look at the options. You can see option A is alcoholic KOH. We know that alcoholic KOH is used for elimination. Then option B is alcoholic KOH followed by NaNH2. Again can be used for elimination. Now option C is aqueous KOH followed by NaNH2. See, now we know that aqueous KOH is not used for elimination. It is generally used to carry out substitution. So that means option C definitely cannot be the answer. Moving to option D, it is Zn in the presence of CH3OH. Alright, so let me tell you, zinc in the presence of CH3OH also cannot be considered as a reagent to be used for carrying out elimination. Alright, in general, whenever we use metals in alcoholic medium, then they usually act as reducing agents. Alright, so that is why we can say that this option D also cannot be the answer. So now moving to option A and B, let's look for the right answer. So let's see this reaction. So here what we have is we have 1,2-dibromoethane, and you can see there will be 2 hydrogens on this carbon, isn't it? Because carbon is tetravalent, you know this. Similarly, 2 hydrogens on this carbon as well, isn't it? Yes. So now when you react it with alcoholic KOH, what will happen? Elimination will take place, and what will get eliminated? It will be the elimination of, yes, tell me. Yes, hydrohalic acid. All right, hydrohalic acid, or you can say elimination of HBr. Clear? And yes, obviously, if this Br is getting eliminated, then let's say this H is getting eliminated along with it. So this HBr will get eliminated. All right. So this is also called as hydrohalic acid. This HX or HBr is called as hydrobromic acid. Clear? So now what you will get is CH, and then Br is there. In fact, let me write this Br in a different way. So you can say CHBr, double bond will come now, and here we have CH2. So this is what you will get as a product. All right. And yes, important thing to understand here is whenever you whenever a reactant undergoes, whenever you carry out elimination using alcoholic KOH, then it is anti-elimination. Anti-elimination. Clear? That means if let's say this Br is present above the plane, then that hydrogen will go which is present below the plane. They both have to be oriented in anti manner. All right. So now this is what we are getting. Now further, what we are doing is we are further eliminating one more molecule of HBr. All right. And how we can do this? Can we use alcoholic KOH now? Yes. No, we cannot use. For the consecutive elimination, that means after elimination of one HBr molecule, further we cannot carry out this reaction, or you can say further we cannot eliminate one more molecule using alcoholic KOH. Why is it so? Because in this case, because bromine has lone pairs on it, and these lone pairs will be participating in resonance, although the participation will be very less, but still due to the participation of these lone pairs into resonance, there will be a partial double bond character between this carbon and bromine. All right, because of which further elimination using alcoholic KOH will not be possible. All right, so there will be no possibility of this reaction. So now what we have to use here is NaNH2. This is what we use in place of alcoholic KOH now to carry out the elimination further. So what happens in this case is you can see this NaNH2 dissociates into Na plus and NH2 minus. Now after this, what happens is this NH2 minus will abstract hydrogen from the terminal double bonded carbon. Let me show it to you. So now let me show it here. So let's assume this is the hydrogen. So this NH2 minus will abstract this hydrogen. All right. And this bond will break like this. Clear? And simultaneously this Br will be taken by Na plus. Or you can say Br will attack on Na. Clear? So thereby leading to breakdown of this bond as well. And as a result, what we will get is CH triple bond CH. Clear? And this is nothing but ethyne. So precisely, I guess it is clear to you guys that what is it that is required to carry out this particular reaction. And therefore you can see clearly option A cannot be the answer, and it is option B that will be the right answer. Hi, let's have a look at this question. You can see in the question we have a reaction given to us wherein we start with acetylene, or you can say ethyne, and it is made to react with NaNH2 in the presence of liquid ammonia, followed by reaction with ethyl bromide. And what we are getting is X. And it is further made to react with NaNH2 in the presence of liquid ammonia and again ethyl bromide. And what we are getting is Y. So we have to find out X and Y. Very easy question. Let us see how to answer. So first of all, what we have is ethyne. So you can see this is ethyne. Now important thing here is this hydrogen of ethyne, these two hydrogens of ethyne, or you can say for any alkyne, the terminal, you can say for any terminal alkyne, basically the hydrogen of the terminal carbon is acidic in nature. Alright, so now when it is made to react with NaNH2 in the presence of liquid ammonia, what will happen is an acid base reaction will take place leading to formation of HC triple bond C negative Na positive, and along with this obviously there will be release of ammonia. Clear? And now followed by this reaction, what we are doing is we are reacting it with ethyl bromide, so CH3 CH2 Br. So now what will happen, this CH triple bond C negative will act as a nucleophile and will attack on the carbon. Let me show it again. Yes, and it will attack on the carbon which is directly bonded to bromine. Why? Because bromine is more electronegative. So this carbon will carry the highest you can say intensity of delta positive charge. So this negative will attack here, and this will be basically a nucleophilic attack leading to release of bromine. Clear? So this is nothing but a kind of nucleophilic substitution here. Clear? And what you will get is HC triple bond C, and then CH2, and then CH3, and NaBr will be released. Clear? So this is what you will get. So and this is nothing but X. So you can see clearly X is but1-ine. Clear? X is but1-ine. So now moving to the next part, that is we have to find out Y as well. So now what we have done is this X is made to react with NaNH2 in the presence of liquid ammonia. So you can see since this but1-ine is also a terminal alkyne, so it will be having an acidic hydrogen. So again the same reaction will take place leading to formation of, you can see, sodium alkynide in this case also, that is sodium butanide. All right, basically let me tell you, this species is called as sodium alkynide, or is in this particular case sodium ethynide. So here you can see Na plus C negative, and then triple bond C CH2 CH3. So this is what you will get. And now upon a reaction with ethyl bromide, that is CH3 CH2 Br, what will happen, again the same type of attack. This CH2 carbon is containing delta positive charge, or you can say maximum intensity of delta positive charge. So this C negative that will act as a nucleophile will attack on this carbon leading to removal of Br, and thus what we will get is NaBr gets eliminated, and the final product that we will get is CH3 CH2 C triple bond C, then again CH2 CH3. So clearly you can see this is nothing but hex 3-ine. Alright, so our Y is hex 3-ine, whereas our X is but1-ine. Let's now match with the options. So now you can see option A says X is 1-butyne and Y is 3-hexyne. Precisely the correct answer. So this is right. And option B is saying X is 2-butyne, Y is 3-butyne. See, for Y it is definitely right, but for X it is not correct. Therefore, option B is not the right answer. Then option C, you can see X is 2-butyne, which is wrong itself, isn't it? So option C cannot be the right answer. Moving to option D, it says 1-butyne, which is correct, and 2-hexyne, which is not correct, which means option D also cannot be the answer. So the only answer to this question is option A. Hi, let's have a look at this question. The question is, yes, we have four options given here and we have to arrange them in the increasing order of acidic character, or you can say increasing acidity order. Clear? So very interesting one. And sorry, it is not increasing order, it is decreasing order. So we have to arrange them in decreasing order of acidic character or acidic strength. Very interesting question. Let me first give you the concept to how to solve such kind of questions. So what you have to simply do is, let's say you have some acid which is Ha. What you have to first of all do is you have to take out H positive. That is, you have to take out the acidic hydrogen, and what you will get is A negative, which is called as conjugate base. Clear? So this is called as conjugate base. Now what you have to just see is the stability of conjugate base. So if the stability of conjugate base will be more, then the acidic character for this Ha will be more. So we can simply say acidic character or acidic strength is directly proportional to the stability of conjugate base. So this is the simple concept. So let's do one thing. Let's first form the conjugate base from these you can say alkenes, alkane and alkynes given to us. So now let's say for alkyne, let's say first of all we'll do. So I'm taking an example of let's say ethyne. So for ethyne, you can see we have CH triple bond C, then negative charge, and this will be the conjugate base of ethyne, or you can say alkyne. Clear? And then we have alkene. So alkene, I'm taking the example of ethene. So if you make conjugate base, what you will get? You will get this particular molecule as the conjugate base of alkene. All right, basically ethene in this case. And then let's make the conjugate base of alkane, which I am taking here as ethane. So it will be CH3, then CH2, and there will be a negative charge here. So now we have to just compare the stability of these conjugate bases. So now first thing that you have to always check is whether the negative charge bearing atom of the conjugate base is same or different. If it comes out to be same, then you have to check the hybridization of that atom. So here you can see the negative charge carrying atom is same, which is carbon in all the three cases. So what you have to now do is you have to check the hybridization. Now for the first case, that is the case of alkyne, the hybridization of this carbon is sp, and I'm very sure by now you already understand how to find or calculate hybridization. Similarly for this one it is sp2, and for the third one it is sp3. Now what we have to see is you can see what we have to do next is we have to find the percentage as character. We know that for sp hybridization the percentage as character is 50%. For sp2 it is 33.3% approximately, and for sp3 it is 25%. Also we know that more is the percentage as character, more will be the electronegativity. All right, and always remember, whenever a negative charge is present on a more electronegative atom, then it will lead to more stabilization. Clear? So here you can see clearly in case of ethyne, that is alkyne, the negative charge is present on a more electronegative atom, because this carbon here is sp hybridized, which means more percentage as character equals to 50%, and hence it will be most electronegative among these three, and therefore the most stable conjugate base will be formed by ethyne, that is alkyne, and hence alkynes will be most acidic among these three. Moving to the next two options, you can see in case of this alkene, that means in case of ethene in this case, since it is sp2 hybridized, the carbon of ethene will have more electronegativity with respect to the carbon of ethane. Clear? Which means the conjugate base formed by ethene will be more stable as compared to the conjugate base formed by ethane, and hence the acidic character of alkene or the ethene in this case will be more than that of alkane or the ethane in this case. And that means the order has to be alkyne most acidic, followed by which is alkene, and the least acidic one is alkane. So let's match with the options. So you can see in option A, the correct order is given. So option A is the answer. In option B, obviously this order is not correct. We know that alkynes are supposed to be most acidic among these three. So this is wrong. Now in option C, alkane is you can see shown to be the most acidic one, which is not right. So this is wrong. And then none of these, there is no chance of none of these. So you can see option A is the right answer to this question. Hi, let's have a look at this interesting question, and in the question you can see what we have to find out is we have to find out which acid upon electrolysis, basically we have an acid, so for which acid, the sodium salt of that acid upon electrolysis will give you acetylene. All right, so here you can see we have to find out the acid for which the sodium salt upon electrolysis will give you acetylene. Very interesting question based on call-based electrolysis. All right, so let us understand. And yes, you can see here the options are scary. Option A is fumaric acid, option B succinic acid, option C is oxalic acid, and option D is adipic acid. Now the first hurdle in this question is, if you do not know the structures of these acids, then anyways you will not be able to solve it. So the first important thing is you should know the structure of these acids. All right, so let me tell you the structures first of all. All right, so first of all, let's do for fumaric acid. Let's do for fumaric acid. So now this fumaric acid has a structure like this. You can see here we have C double bond OOH. Here we have C double bond OOH. And you can see this is pi bond. Clear? So now this is fumaric acid. Basically you can see trans isomer. Clear? So now in this case, if we take sodium salt of it, what we will get is, you can see the sodium salt of this fumaric acid will be, let me write it for you, O negative Na positive, and here also O negative Na positive. Clear? So now you can see when this sodium salt undergoes electrolysis, all right, then what will happen? Let's find out the product. So now first of all, let me tell you, when this is taken as an electrolyte, then at anode, what will happen is, this fumarate ion basically will go and will get discharged first. All right, it will go and get discharged preferentially. Clear? So now what will happen, we have aqueous solution of this basically sodium fumarate, wherein the fumarate ion will go to the anode, and we know that at anode oxidation takes place, and oxidation is loss of electron. Clear? So when this particular fumarate ion loses electron, it will lose it from both of the oxygens. Clear? So now it will be loss of 2 electrons, wherein 1 from each oxygen, and what we will get as a result is C double bond O with the you can say 1 electron on this. Just a minute, let me represent it properly. Okay, so now you can see what we will get is this particular molecule. So this is C double bond O and O radical, and C double bond O and O radical. Clear? So now as soon as we obtain these radicals, what will happen is this basically this electron will shift here like that, and leading to breakdown of this bond. All right, and this will be a homolytic cleavage. So now similarly from this side also, this will move here, and there will be a homolytic cleavage of this bond. So what we will get as a result, we'll get 2 molecules of CO2 gas that will get evolved at anode, and what we will be left with is CH double bond CH, and 1 radical here and 1 radical here. So this is a case of diradical, and whenever you see diradicals, generally what happens is they form product by combination, wherein these two will now form a bond, and what you will get is this particular product, and this is also gaseous in nature. So we will get acetylene here, or you can say ethyne. Clear? Liberated at the anode. So clearly you can see with fumaric acid you will definitely get acetylene. So this is definitely the right answer. But let's look for succinic acid and oxalic acid also. And one more important thing, I have not told you the product at cathode. So let me tell you at cathode what will happen. Basically, since it is an aqueous solution, so water will be present. So in place of sodium, water will go to cathode and gets preferentially discharged, thereby liberating hydrogen gas at cathode. Clear? So now let's look for the next acid, that is your which one? Succinic acid. So it is very simple, very basic case. And let me tell you a trick also in order to save time to solve for rest of the cases. It is very simple. Let me tell you the trick. So the trick is basically you just cleave this bond and this bond. That means you have to just liberate or release CO2 molecules. All right, so now if you break this bond, obviously you can see from here CO2 can release, from here CO2 can release, and whatever is left, you can see here this part is left. So whatever is left, you have to form radical on both the ends, and then you can simply join these radicals. So let us use this particular trick to find out product in case of succinic acid. All right, so for succinic acid, if you see the formula, then it is like this. So you can see O negative, and I'm straight forming the sodium salt, and here also COO negative and Na positive. Just a minute, I have written it opposite. Just a minute, guys. Let me correct this. Okay, so it has to be ONA positive. All right, just a minute. Yes, so here you can see Na positive. Clear. So now you can see what you have to do is remove from here, so that we get two CO2 molecules at a node. Then what is left is this straight line. That means we have radicals on both the ends, and then you have to simply join them, and what you will get is like this. So let me show the carbons also and hydrogen also. So now you can clearly see what we are getting is ethene and not ethyne. So definitely this cannot be the answer. Similarly, let's look for oxalic acid. So let me tell it to you here only. So oxalic acid is this molecule. So I'm straight forming the sodium salt of it. So this is the sodium salt of oxalic acid. So clearly you can see in case of oxalic acid, you will obtain just and just CO2, because if you break it from here, then only you will be able to get two CO2 molecules, and these two CO2 molecules will be the only product in this case. So this is also not the answer. Moving to option D, that is adipic acid. So now adipic acid is a 6 carbon acid. All right. So let me tell you the structure here. Okay, so here we have C double bond O, and yes, again I am simply drawing the sodium salt directly. So O negative, Na positive. Clear? And you can see 1 2 3 4 5 6 here also, C double bond O negative and Na positive. Clear? So now again let's use the trick. So you have to break this, you have to break this. Whatever is left, let's write it. So this is what we are left with. Clear? So now what will happen is, you can see, since we are getting a diradical, we just have to join them, and what you will get is a cyclobutane as the product. Clear? So this is what you will get in case of adipic acid. So definitely this also cannot be the correct answer, and hence the only answer to this question is option A, that is fumaric acid. Hi, let's have a look at this question, and the question is, you can see in this we are given a sequence of reactions, and you can see for the given reactions A and B are the major products. As you can see here, for the sequence, for the first reaction A is the major product, and for the second B is the major product, and for the third one C is the major product. Now what we have to find out is the major product C. All right, so we have to find out the major product C. Very interesting question, and always remember these kind of questions are literally very interesting, and they will help you revise multiple topics in one go. So let's understand what will happen here. So first of all, you can see here we are using KMnO4. We know that KMnO4 is an oxidizing agent, isn't it? So what it will do is it will oxidize this molecule, although it is alkane, and we know that generally it do not oxidize alkanes. But when you have a 3-degree carbon present and one hydrogen attached to that 3-degree carbon, then it oxidizes such alkanes to form alcohols. So what you will get in the first reaction is this particular product, CH3 and then CH3, and what it will do is it will break this 3-degree carbon hydrogen bond, and in place of it, it will add OH to both the parts. All right. So what you will get is you will get an alcohol along with water. So water is released along with formation of alcohol. So now you can see this is a 3-degree alcohol that we are getting here. Now the next step is you can say reaction with H plus, which is nothing but reaction of alcohol in acidic medium, which leads to dehydration. Dehydration means removal of water. Clear? So here when you heat in the presence of acidic medium, then alcohols lead to removal of water, thereby forming alkenes. All right. So let me tell it to you. Although there is a mechanism for this particular process, but okay, let me tell you the mechanism only. But let me first tell you the product. So the product here will be like this: CH2 double bond C, and then CH3 and then CH3. So this will be the product basically. But let me tell you how this product is getting formed. It is very simple actually. So let's see. So here we have CH3 and then C, and then we have CH3, CH3, and we have OH. So first of all, what will happen? This H positive, we know that oxygen carries lone pair of electrons. So these lone pairs will be donated to H plus first of all, thereby forming protonated alcohol. All right. So what we will get is a protonated alcohol. So you can see this will be the structure for protonated alcohol, OH and H with a positive charge on the oxygen. So now you can see this protonated alcohol is a very good leaving group. All right. So this will this bond between C and O will cleave, leading to release of water, and what we will get is a carbocation. So now you can see what we are getting is a carbocation. Now you can see this is what we are getting. So now once we get the carbocation, what will happen? You can see the very next carbon, which is sp3 hybridized. So let me represent it here like this, CH2, and then we have NH here. So from this very adjacent carbon, the hydrogen will get removed. And how it will get removed? Basically, you can see from acid we have used positive part, that is H plus. But obviously there will be some conjugate base as well that will be present in the system. So this conjugate base will basically abstract this hydrogen, all right, leading to breakdown of this bond. Not this one, sorry. Let me correct this. Yes, it will lead to breakdown of this bond such that the negative charge will come onto the carbon. Clear? So therefore what we will get is CH3C double bond CH2 and CH3, and there is a release of, you can say, HA, or you can say HA will get generated again. Clear? So this is how the product is formed in this particular case. Clear? So now we know B is nothing but an alkene, that is an unsaturated hydrocarbon. Moving to the next part, now you can see we are reacting this alkene with HBr in the presence of a peroxide. So just try to focus, try to regain your memory, try to think what you will get. We know that when HBr is made to react with the peroxide, then anti-Markovnikov's addition will take place. It is known as Kharash effect or peroxide effect. And what you will get is, definitely since anti-Markovnikov addition is going on, obviously what you will get is the bromine, or you can say the negative part of this addendum, which is nothing but bromine, will attach onto that particular double bonded carbon which carries more number of hydrogens. So now here you can see this carbon is carrying 2 hydrogen and this one is carrying no hydrogen. So definitely Br will get attached to the carbon bearing 2 hydrogens in this case, and the product therefore will be CH2Br, and here you can see CH and then CH3 and CH3. So this is nothing but your product C. Clear? So let's now match with the options. An important thing here is this Kharash effect proceeds through free radical addition mechanism. Clear? Wherein we will be having 3 stages: initiation, propagation, termination. Clear? So let's now match with the options. So you can see option A is saying that Br is attaching to the carbon which is bearing 2 methyl groups. So here you can see they have removed one of the methyl groups itself. That means they have reduced the number of carbons, which is not possible in this case. So this is definitely not the right answer. Moving to option B, again you can see here they have attached to the carbon bearing 3 methyl groups, which is not possible. So this is also wrong. So moving to option C, again not correct. But option D you can see is exactly matching with what we have found out. So that means option D is the right answer to this question.